Everybody. Well, I hope you're doing well today. I hope to see some more of you at our Google Hangout at the end of the week as well. It'd be great to see you. You can ask any questions you have about the class. Most of all, though, I hope you all are doing well, staying healthy and staying safe. There are a couple stories now of younger folks that have been influenced by this virus, so you need to take it very seriously and be very careful, and then we'll get through everything together. So last time in class we talked about what's causing biodiversity loss, and that there are three main factors leading to that: introduced species, direct exploitation or overharvest, and then habitat destruction. But I did want to share some reasons for hope. We read that Leopold tribute to the passenger pigeon, saying that maybe it's a distinguishing characteristic of what it means for us to be human that we can recognize species going extinct as a bad thing and help to save them. Here's a couple examples of that being the case. Giant panda populations have been slowly increasing from being in a bad state several decades ago. Mekong River dolphin also, we've been seeing some increases in population for the first time in a long time. And then the mountain gorilla, in the last half century or so, this population has doubled. So I just point this out to make the point that we are in fact having an impact on saving some of these species. So we just have to keep our determination and hard work, and we can keep species from going extinct. Something we can do. Yeah, so this is the biosphere as we talked the other day, where all species occur, at least that we know of so far. But it's also interesting to look at the Earth from a water resources perspective. And when you look at the globe in this particular perspective, think a little bit about what you can see about water. Probably notice all the blue, which of course is the ocean. That's salt water. You might notice the clouds, water moving around on the air currents. And you might notice the polar ice cap, Antarctica, there in the south as well. So we have ice that's water that's frozen as ice on our planet, in a planet as well. Just a couple stats for you. We have lots of water on Earth, right over 1.4 billion cubic kilometers. I can't even wrap my head around how big that number is. But of that, only 2.5% of it is fresh water. And less than 0.5% is active in the water cycle. That means it's coming down to the Earth in precipitation, going up as evaporation, and so on and so forth. So the real point here is that, look, we've got a lot of water on this planet, but not all of it is a resource. In fact, a very small amount of it we can actually term a resource. So this is the water cycle. You've probably been learning about it since middle school. Did you guys ever hear the water cycle song? It goes, I can't remember all of it, but it's something like, it comes down in precipitation, yes it does. It comes down in precipitation, yes it does. It comes down in precipitation. It goes up in evaporation. It comes down in precipitation, yes it does. There, I guess I kind of remembered it, huh? All right. You can all sing it on your own time. But really what we're interested in now as environmental scientists is the question of how does human activity affect this water cycle, right? So when water comes down to the surface, it can go one of three ways. It can run off the surface as surface runoff into our rivers and streams. It can soak down into the soil by infiltrating the soil, percolating down to the groundwater. Or it can go right back up into the atmosphere, either as evaporation, or if it gets taken up into plants through their root systems, it can leave via the stomata in their leaves as transpiration. So water's moving around, and this whole water cycle is driven by what? Yes, that's correct, the sun. Good job. So here's a case study looking at four creeks in the Dallas-Fort Worth, Texas area. And it's been one of the fastest growing suburban areas of the United States. And so we can ask ourselves, how has the surface runoff in this area, the volume of water in these creeks, changed in the last 40 years? And so this is a case study I worked on when I was teaching at Austin College in Texas with Drs. Peter Schultz and David Baker. So here's an aerial photo which has been calibrated to show reflectance levels. So basically the bright colors you see are areas on the land that are high reflectance. So think like cement, concrete, blacktop. So these are urban areas, these very bright sort of light areas to the middle bottom part of this image. And all the red that you see in this image is vegetation, right? So red is actually green. And there are 4 watersheds in this area, right? So the watershed is all the land in which if a droplet of water falls to earth, it will drain to a single point. So we, for instance, in Asheville are in the French Broad River watershed. So any drop of water that falls to ground in Asheville is ultimately going to find its way into the French Broad River. So we've got 4 watersheds here. Now at the downstream end of each watershed, you see the dot. There is a gauging station managed by the U.S. Geological Survey that measures the amount of water flowing out of this watershed. So the amount of water, the stream discharge as it leaves the watershed. All right, so I'm going to show you a series of 4 graphs, right? So we've got time on our x-axis going, in this case, from the 70s up to 2005. And we have discharge, the amount of flow coming out of the watershed on the y-axis. And then each of those diamonds is a year. So here's Clear Creek. So when you look at those data, does it look like there's any consistent trend over the years of the values getting higher or lower? Well, we can use statistics to test that. We can calculate what's called the correlation coefficient. And when we do that, R, which is our correlation coefficient, is negative 0.195. Now, if there's no correlation at all, the correlation coefficient equals 0. If the correlation equals 1, it's a perfect positive correlation. As one variable increases, the other one increases. If R is negative 1, it's a perfect negative correlation. As one variable increases, the other decreases. But how do we know if it's a significant correlation? Well, we can generate statistically the probability of the pattern that we see given random chance. So that p-value there represents the probability of getting this pattern based on random chance. And so it's saying there's a 37% chance of getting this pattern based on random chance. Now, statisticians and scientists have a cutoff value. They say if the p-value gets below 0.05, then we conclude that the pattern is not due to random chance, and in fact, it's statistically significant. So when the p-value gets below 0.05, it means there's a less than 5% chance of getting our pattern based on random chance. And we determine that, in fact, there's a significant pattern going on. So with Clear Creek, there's a very weak correlation between year and stream discharge, and it's not statistically significant based on the p-value above 0.05. Well, what about Little Elm Creek? Think there's something going on there? Again, a very weak correlation. R is very close to 0. Our p-value is 0.49, so not a statistically significant correlation here either. Denton Creek, what do you think? Not much happening. Again, even a weaker correlation coefficient, a p-value of 0.6. Well, what about Rowlett Creek? Gosh, if you look at these data points, they seem to be getting higher as we move from the 70s into the 21st century. And if we put it through our statistical machine, yeah, in fact, our p-value is less than 0.001. What that means is that there's a strong positive correlation between year and stream discharge. So that means that over the years, the amount of water coming out of this watershed has been increasing. We can use another statistical technique called linear regression to plot the best fit line that shows what this relationship looked like, and that's that white line there. Well, all right, so what's going on in Rowlett Creek, right? All these other creeks didn't have a significant pattern, but Rowlett Creek did. What's up? So you can think about what would cause there to be more water coming out of a watershed in general, right? And then see if these could be possible hypotheses to explain our observation of increased stream discharge in Rolette Creek. So think about what can increase annual stream discharge. This could be all kinds of things, right? More rainfall would cause it to increase. Could that drive this pattern in Rolette Creek? Pretty unlikely, because the other watersheds were close to it, so why would there be increasing rainfall in that one watershed, not any of the others? Now, snowmelt can play a role for rivers that have headwaters up in the mountains, but that's not likely to be the case in North Texas. Now, removal of vegetation. Removal of vegetation. When you take vegetation off the landscape, it reduces the amount of water that goes up in transpiration, and it allows the water to rush off faster into the rivers. So that might be something going on there. And then wetlands. We talk about swamps, marshes, those kinds of things. Those can be real important because they function as sponges, so that when the water comes down in rain, it can get soaked up by the wetlands and not go slamming into the rivers as fast. So maybe that could play a role. So now let's think about these relative to Rolette Creek. All right, so here's that image from 1974. Okay, so focus on the urban area. That's that bright, sort of lightish white to gray colored splotch in the lower part of the image here. So that's the Dallas-Fort Worth Metroplex. Now look in 2003. Now the shading's a little bit different. Atmospheric conditions cause that, but there's certainly a lot more urban area here than there was back in the 70s. And if you look at the Rolette Creek watershed, look all of a sudden at how much developed land is there in Rolette Creek. Certainly a lot less red there, and a lot more of the high reflectance surface. So it looks like there's plants and there's forest and wetlands and things that are being replaced with developed land. And so it looks like probably what's happened in Rolette Creek is that there's less water getting down to the ground and more running off into the rivers and streams. In fact, Rolette Creek is located on the in the McKinney, Texas area, and the town of McKinney, Texas is what was the fastest growing suburban area in the U.S. for quite a while. So there's a lot of development going on in that watershed, and it's affecting the water cycle. So here's some data from an example in Canada where they looked at some data. On the left is a pre-urban area, and then this to the right is urban. And if you look at 100% of precipitation that falls down, you look in the forested watershed to the left, about half of that water goes into the ground, 40% goes back up to the atmosphere through evaporation and transpiration, only 10% is surface runoff that winds up in the rivers and streams. Well, now you look at an urban system, and all of a sudden, only a third of it is going into the ground. And look how much is going to surface runoff, about 43%. So the way the water cycle works after an area has become urbanized is that we have a lot less water getting into the ground, and we have a lot more water running off the surface. Okay, so what do we use the most water for in the U.S.? This is when I'd ask you all to think about what it is. This is data from the U.S. Geological Survey. And they broke it down in these 7 different categories. So irrigation, electric power generation, the public municipal water supply, water needs by industry, livestock and aquaculture, domestic water besides the public supply, so this would be like well water, and then mining. So think about which of those you might imagine we use the most water for. Yeah, so it turned out that 80% of the water we use is for irrigation and thermoelectric power. So to me this is really interesting because it points out the impact that agriculture has on so many of our environmental processes. So we take a lot of water to put on land to grow the crops that we eat. Similarly, our electricity usage is about almost 40% of our water. So if we use less electricity, we need less water. So groundwater, that's water that has percolated and infiltrated down below the surface into aquifers. Groundwater is used for about a quarter of the U.S. water withdrawals. And we can look at different parts of the U.S. where we're depleting water at fairly quick rates. These are millions of gallons per day, right? So between 20 and 500 is moderate. And then those areas with the darkest brown are critical, where we're really taking water out of these lands a lot faster than it's getting into the ground. So it's a trick question. If I were to ask you, what would be the rate of groundwater depletion if we were using it renewably? And of course the answer would be that we wouldn't be depleting it, right? We'd be using it at the same rate that it's supplied. So the fact that we're depleting these groundwater resources tells us that this is not a renewable resource in these areas where groundwater depletion is occurring. I don't know if you've ever flown over the American West, the California area, and you've seen these strange green circles out in something that looks like a desert. And that's a signature of center pivot agriculture, where you have these big machines that roll on wheels and irrigate crops. And so you look at areas that haven't been irrigated and it's brown, right? That tells you how much rainfall is falling in these areas. So where is that water coming from to grow all these crops? Well, from under the ground. So we've been able to use groundwater to grow crops in a lot of places that we wouldn't be able to normally. However, that groundwater is not being replenished because there's not a whole lot of water coming down from above, and so this is not very sustainable. And remember, when we talked about agriculture moving forward, one of the things we need to focus on is efficient use of water, right? Spraying water up into the air is not an efficient use of water. This is an area where a lot of that agriculture is going on, and the Ogallala Aquifer is being drained pretty rapidly. So in some areas it's being removed 40 times faster than it's being replaced. Now it's interesting. So aquifers are these underground layers of water. They're not like underground lakes. It's not like a cavern. You couldn't like boat or like go water skiing on these underground lakes. It's permeable rock that's saturated with water, right? But the reason we have so much water under the ground here is that this area used to be a lake tens and tens of thousands of years ago. That water remained underground, and so we're taking it up now in the Midwestern United States to irrigate our crops. And you look at the thickness of this water layer, right? In some places it's 300 meters. It's a lot of water, but when we're using it up 40 times faster than it's being replaced, certainly the amount of water under there is going to become less and less. So one of the ways we can be a little more efficient is with drip irrigation. So you saw that center pivot agriculture picture earlier where it's spraying the water all over. Well, we can hook up devices to this that drip that water down onto the ground so we can use water more efficiently. So surface water, right? This is water that is flowing in our rivers and streams, and it's in our lakes. So Sandra Postel, in a really interesting article, estimated that humans use over half of all the surface runoff on the planet that we can get to. So we do things like put it into canals, like in this particular image, and send it to places that it's needed. And so you can see this canal running through the desert, right? You can only imagine how much water is being lost by evaporation here. And if we look at the distribution of runoff, and then we compare it to where the most people live on the planet, it's interesting. So we can break it down by continent: Europe, Asia, Africa, and then we can look at North Central America, South America, Australasia, and Oceania. So the total river runoff is in the first column. Then the percent share of the global river runoff is in the second, actually the third column from the right. And then on the far right is that region's share of the global population. And it's interesting to me just to highlight a couple extremes here. So in Asia, it just has a little bit over a third of the share of the world's river runoff, but going on 2/3 of the world's population. So that's a place where there's not going to be much surface water to go around. South America is the opposite case. They've got 1/4 of global river runoff, but only about 5 to 6% of the global population. So South America is a place where water is not going to become scarce as quickly as in Asia. So when I was in Nepal, I was doing research on the Kali Gandaki River, as I mentioned, and there was a spot where this human appropriation of surface runoff was really obvious. So the yellow line that's going from left to right across the middle of this image is the border between Nepal and India. So Nepal is to the north, India is to the south. And our study sites are these little pins in Google Earth. But if you look at the river flowing down from the upper right, and then it flows down toward the lower left, it comes up to a dam. There's some writing going across the river there, and then downstream from that dam, see how little water is left in that river? Well, what's happening, if you can see, is there are canals on either side of this dam, one that heads down from the dam and one that heads up and around. And so both of these are water diversion projects that take water to India. Here's a closer picture of it, and again, you can see that this dam, this is during the dry season, so that this dam is there, and then you have the diversion that takes water to both sides and eventually to India, where farmers will use it to irrigate their crops. So it takes a lot of water out of the river. You look how much less water there is downstream from the dam, or the barrage as they call them in Nepal and India, than there is up above it. Pretty dramatic. This is what the view looks like from above. We had a water temperature data logger here to see how the water temperature was affected by this dam. It was kind of interesting. Wherever you have dams like this, the stream water warms quite a bit because you have just all this water sitting out in the sun, and it's warming. So when it comes down over the dam, it's warmer water than it was before. Got some water buffaloes coming in to drink at this place, so it's a resource. The people definitely are able to use this lake as a resource. They can water the, and there are lots of fish as well. There's me on the left with some fish that this guy had caught and was selling, and the person on the right scaling some fish to cook up. Another interesting thing about this, I don't know if you can notice, but if you look, the river kind of flows again from right to left, and then it kind of hits that wall and comes straight down. Well, you can see the remains of what used to be the old river channel there. If you can see, there are those darker areas. It kind of looks like almost like a horseshoe kind of thing. That's where that river used to go until they built this big barrier right there, that straight line. It goes up toward the town of Kudia, and it was literally just a wall, a big barrier that was that was built there to protect all of those villages from the river. So not only has the Indian government here diverted water to these irrigation canals, it has also built a big barrier to literally move the channel of this river. So a pretty dramatic alteration of a river here. This is what it looks like downstream, a lot less. This is us, myself and Amar Gurung, sampling fish downstream from this dam. And there's the payoff. When you catch the fish, you can get them cleaned up and fried, and you can have a little snack. Good stuff. All right, so we have instances through history which have shown the impact of people on water resources. This is the Aral Sea in Eastern Europe. So it was located next to some areas that were used for actually cotton production in the former Soviet Union. So cotton is a water-intensive crop, and so water was taken from the Aral Sea, but it's not an area that received much rainfall. So as a result, the sea got smaller and smaller, and ended up ultimately beaching ships like this one up on the right. It's a pretty dramatic example of overuse of water in an unsustainable way. Anybody been to the ancient city of Angkor, Cambodia? It's an amazing place. I haven't been, but this city lasted for 6 centuries, which is a pretty good run. 600 years. How long has our country been around? About what, 240 years, something like that. So 600 years. That's not bad for a city to last. It was the largest pre-industrial city in the world, and the city itself is laid out on sort of the spokes of a wheel, where there's this big central lake, and then the spokes that go out are these canals. And it was a really complex water distribution system. So some researchers used dendrochronology, this practice of taking tree cores and then looking at the spacing of the tree rings to learn about what the climate was like through history. And some of these trees are thousands of years old. So you can take core samples of those trees and reconstruct the climate going back years and years and years. Well, when these scientists did that, it turned out that the city of Angkor's decline corresponded with a climatic shift to a drier climate. It was a time called the Little Ice Age. Now, the Ice Age is drier because there's more water captured in the ice. So there's less water to move around in precipitation in the water cycle. So ultimately, it was access to water that led to the decline of the ancient city of Angkor, Cambodia. Similarly, in Asia, Genghis Khan, who you may have heard of, who conquered the largest contiguous land empire ever realized in history. Some authors were studying the climate of Siberia in the time of Genghis Khan. So the Siberian pine, again, is one of these trees that can live over 1,000 years. And so you can take a core of it, you can drill a core out of this tree, and you can learn about what the climate was like during this time. So it was really interesting. So Dr. Amy Hessel at University of West Virginia headed up this analysis. So again, the 13th century Mongol Empire, the largest contiguous land empire in world history. But based on their data, it looks like in addition to Khan being an amazing soldier, he was also very fortunate, because this was a time when that area was warmer with a lot more precipitation than was usual. 15 consecutive years of above average moisture in central Mongolia, and this coincided with the rise of Genghis Khan, or Chinggis Khan as it's properly spelled. And this hasn't happened in the last 1,000 years. So remember the variables that predicted high levels of productivity in terrestrial ecosystems? Temperature and rainfall. So this time of warmer weather with more precipitation meant that those grasslands were very productive, and that favored being able to feed your horses and other livestock and growing other crops as well. So this kind of productivity maybe contributed as much to the Mongol political and military power as Genghis Khan's military prowess. So it's interesting that in the early 21st century, they note that the drought in central Mongolia, on the other hand, was the hottest drought in the last 1,000 years. So this is concerning because this warming is also unprecedented. It's going to be affecting the environment. So hopefully we can learn from the past and be prepared for changes in the climate as we move forward. All right, one final example of how water affects our society. So the Arab Spring was this event that led to protests across much of the Arab world for political reform. There's a research project done by Colin Kelly, who's a UNCA graduate, and it related Arab Spring to agriculture and climatic shifts. What Kelly found were a couple things. First of all, this was in Syria, that the government had supported a policy of unsustainable agriculture, right? And so this led to a decline in groundwater. Just like how we were talking in the U.S. with declining groundwater levels, right? So, all right, don't have groundwater. Well, we'll just rely on rainfall. Well, in this particular area, rainfall occurs in the winter and is highly variable. So a severe drought came along in 2006-2007, and this led to agricultural collapse. The severity of this drought cannot be explained using only non-anthropogenic mechanisms. Now, if you know what that means, non-anthropogenic means not having to do with humans, right? So essentially, the severity of this drought can only be explained using human impacts. Okay, so due to this agriculture collapse, what happens? Well, people in rural areas all of a sudden are not able to feed themselves, so this led to 2 million people migrating to urban areas. That, therefore, created civil unrest and ultimately rebellion. So it just shows, once again, how our society is so susceptible to these climatic events, which in this case were tied to water, as well as unsustainable human development. So, in the environmental realm, water is a very important currency, and learning how to manage it and sustain it is really going to be key for us being able to live sustainably into the future. So I've just highlighted a couple issues with water use globally here. And so these are all things we're going to have to understand and work to develop renewably moving forward.